Hi everyone. We're going to solve a problem now where you're actually having a electric potential difference accelerating a beam of electrons, and the beam of electrons will be fired into a fairly uniform magnetic field that has a kind of compact size, so there's size limitations of it, and the magnetic field is going to be running parallel, or excuse me, perpendicular to the velocity of the actual electrons, and we're asked to basically calculate what kind of motion it's going to be experiencing, how much the force is, what the velocity is once it gets out of the 500-volt potential, what the path is going to follow, and whether it has enough room to actually follow that path. So let me turn on my document cam so you can see the actual question. I've got it as a thumbnail too for the actual video so you can see the question there. And basically what you see is we have a 0 volt to 500 volts, and electrons are being accelerated through there. Of course, electrons go from low voltage to high voltage, so it'll be accelerated through here and they'll reach some maximum speed, and then right there there's no more voltage change, so the speed should more or less be the same, mainly because the force acting on the electron when it's in a magnetic field is in fact always perpendicular to the velocity, so it can't speed it up or slow it down. So what we're going to see is it's going to come in and we're going to try to predict, what kind of motion we experience, how fast it is when it gets here, and so on. So if electrons are accelerated by a 500 volt potential difference and then sent into a magnetic field of 0.011 Tesla perpendicular to their velocity, A, what will their speed be? So that's the first part, is what will the speed be when it gets right here? B, how will the direction of travel change? C, what type of path will they follow? And D, if the uniform magnetic field only extends 5 centimeters above, below, and beyond the 500 volt potential, will the electrons complete their path? So obviously I know a little bit about what the path is going to be. That's why I asked that question that way. So this question should help you figure that out. What we do know is that the force is given by QV cross B. So if the electrons are going from left to right and the magnetic field, as the green circles show, are pointing out of the page, then we know QV, since Q is negative, QV points in the opposite direction of V. So it should point this way. And with QV that way, that forces me to turn my palm up so that my middle finger can point up towards the direction of B. And then obviously that's going to force the electrons to be traveling upward. So the beauty of that is you see that the electrons, when they're right here traveling this way, they experience a force. So that's the little velocity right there. They experience a velocity this way, but they're going to experience a force perpendicular to it that way. So then maybe they're moving, say, in this direction. But again, QV cross B gives that their force will be again perpendicular to that velocity. So I think you can see that's going to continue as the velocity direction changes. The force direction is going to continuously be perpendicular to that path. So really, if the area is big enough, the electron is going to try to go in a circle. Now, if the electron happened to be not only perpendicular to the electric field, magnetic field this way, but maybe had a little bit of velocity parallel to it, then that velocity would be unaltered completely. So the electron would actually spiral around like this and come up in a helical path. So what we're going to do now is calculate part A. What would that velocity be? So what we know is that the potential difference caused by the 500 volt potential, U, is equal to the charge times the voltage. And that charge, of course, just leaving out the signs but dealing with the magnitude, that charge is going to be the electron charge times the voltage. That electric potential is going to be electron charge times that voltage. And that, assuming the velocities are non-relativistic, would just be equal to 1/2 m, the electron, times the velocity squared. So we can see that the velocity is going to equal 2 times the electron charge times the voltage, divided by the mass of the electron, and then of course we have to take the square root of that, and that would give us our actual velocity. So in this case, the velocity would be square root 2 times 1.602 times 10 to the negative 19th coulombs times 500 volts, or you could of course call that energy 500 electron volts, but we're using joules here. And then the mass of the electron is 9.109 times 10 to the negative 31st kilograms. And then of course we're going to take the whole square root of all that thing, and that should give us the actual velocity. So 2 times 1.602 e to the negative 10 times 500 divided by 9.109 e to the negative 31 in parentheses. And then I'll take the square root of all that mess. And I get 1.32 to, let's go ahead and call it 6 times 10 to the 7th meters per second. So we see we're about a factor of 20 smaller than the speed of light. That's probably fairly reasonable for use of non-relativistic equations. So that's our answer to part A. It's going to be traveling about 1.32 times 10 to the 6 meters per second, or 10 to the 7, excuse me, meters per second. Part B, how will their direction of travel change? Well, as I pointed out earlier, when the electron's going this way, the velocity, of course, is this way, but QV is in fact that way, so that the and the magnetic field is this way, pointing out. So QV cross B gives us a force that actually points upward, so the particle is going to tend to deviate upward. Then, when it starts deviating upward, we again have a QV, a V that's this way, a QV that's this way, a B that's this way, and again we're going to get a force that's perpendicular to that, so that's going to tend to rotate it this way. And even when you get a velocity going, say, this way, the QV, of course, is this way, the magnetic field is still this way, so the force is this way, again perpendicular to the path, so you see it's going to arc around like this and try to make a circle. So that's how the direction of travel will change. That's part B. And part C, what path will it follow? Well, ideally, if the electromagnetic field area is large enough, it'll follow a complete circle. It'll come in like this and make a circle. So D, if the uniform magnetic field only extends 5 centimeters above, below, and beyond the 500 volt potential where the electrons complete their path. So really what we're asking is how big of a circle would it complete if this magnetic field were in fact uniform. So if we allow the force, which by the way, since force is QV cross B and V are perpendicular, even QV and B are perpendicular, we know that the magnitude of the force really is going to be, which we can also write as just F, is just going to be equal to QVB, which equals the electron charge, V, we already have that, square root 2eV over m sub e, times the magnetic field. And of course, if that isn't a circle, then that force must be responsible for the centripetal acceleration. So we know that that should be equal to E times the square root 2eV over m sub e, times B has got to equal m, the mass of the electron, times the square of the velocity, which is this quantity again, but now we're squaring it, 2eV over m sub e. And then all of that will be divided by the r. And I think you can see when we have that, the m sub e's cancel out with one another on this side, and we can solve for r as follows. So we have r is equal to 2EV over B times the square root of M sub E over 2EV. So there's my E, pulling the R over here. I've got 2EV, that's from that. I've got this B came over here. I also need this electron charge to come down here, so I'll have the E down here as well. And then I have the 2E and the V over here already existing. So we can make some more cancellations. This E will cancel out with that E. We can actually pull some of the stuff inside, for instance, and get that when I pull something inside a square root, it actually has to become squared. So I'll get the square root of 4 M sub E V squared over 2 E V B squared. Which now you can see some more cancellations. This square is going to cancel out with that. This 4 is going to cancel out with that, leaving just a 2. So I'll ultimately get R should be equal to the square root of 2 M sub E V over E V squared. So hopefully that all works. Let's look at the R. So R will be the square root of 2 times 1.602 times 10 to the negative 19th coulombs. Well, heck, that's the charge, not the mass. So I kill that. Let's write 9.109 times 10 to the negative 31 kilograms times 500 volts over the electron charge 1.602 times 10 to the negative 19th coulombs times the magnetic field squared, which would be 0.011 Tesla squared. Take the square root of all that. That should give us our answer. Let's check it out. 2 times 9.109 exponent negative 31 times 500 divided by 1.602 EE negative 19 times 0.011 squared in parentheses equals all that. Take the square root of all that stuff. And I get 0.00685 meters, which would be about 0.6 centimeters. So in fact, as soon as it starts going in there, it's going to try to complete a circle of radius 0.6 centimeters or 6.85 millimeters. That's clearly enough distance to try to make the circle, but it's going to actually turn out to be about half the circle before it could actually do it, because yes, it's got 0.68 or 6.85 millimeters from here to here, but it's going to do that and come back out before it pops out. So I hope that helps you understand how to use QV cross B, as well as how to use the right-hand rule to figure out directions, as well as recall how to use Newton's second law, total force equals mass times acceleration, which we used here by seeing the total force, which is QVB, is equal to the mass times the acceleration, which was V squared over R. So I think that helps you solve this, should help you solve the problem. Have a good day.